Today we'll finish on data transmission, going through a few more examples. Where are we? Week 3. Week 3? Week 4. Week 4. 3 more weeks. I think we have 7 weeks before the midterms. So this is week 4, correct? This is week 4. There's another 3 weeks after today. And then you have the midterm. What we've talked about with data transmission is how are communication signals composed. And looking at the very basic form, we can think of communication signals are made up of sinusoids. It's much more complex than the examples we've shown, but the mathematics behind it is that we can consider a signal as a combination of different sinusoid signals. And we've talked about analog and digital data, and we got to some formulations of channel capacity. Now, channel is our link, or it could be more generally a network. Think of a link, communications link. We care about how many bits per second can we send across that link based on the physical characteristics of that link. What limits it? And 2 people have come up with formulations that Nyquist and Shannon that relate the data rate, the maximum data rate for a link, that is the capacity in bits per second, with the physical characteristics of bandwidth. How much bandwidth do we have for our signal? And also take into account some other factors, noise and error rates. We saw with the Nyquist capacity that relates the data rate or capacity is 2 times the bandwidth of our channel. So a particular channel allows some range of frequencies to pass. That range is the bandwidth. If our channel allows us to send between 1 megahertz and 3 megahertz, that's a bandwidth of 2 megahertz, from 1 to 3. So a channel has a particular bandwidth. The Nyquist capacity says it's 2 times the bandwidth multiplied by log in base 2 of the number of levels of our signal that we use. Where we've seen that the basic case is we use 2 levels. We could have, for example, a bit 1 representing by a high voltage and a bit 0 represented by a low voltage, as an example. But we can do more than that. We can have multiple levels. We could have 2 bits, 0, 0, represented by 1 voltage, 0, 1 represented by a second voltage, 1, 0 by a third voltage, and 1, 1 by a fourth voltage. That would be 4 different levels, and we could use that scheme to send signals representing any sequence of bits. The more levels we have, the higher the data rate we achieve with the same bandwidth. So if I have a communications channel with a fixed bandwidth, I cannot change that. One way to increase the data rate, increase C, is to increase M. Choose a scheme that maps our bits to multiple levels, increase the number of levels. But as we pointed out yesterday. Yesterday we said if we have 2 different schemes, the first scheme, let's say, goes from -5 to +5, and if we want 1 bit, we transmit at this level, another bit we transmit at this level. So this is M equal to 2 with 2 different levels. If we take the same space, and use 4 different levels, so between -5 and +5, but separate that into 4 levels so that our signal In this case, we'd have 2 different levels. In this case, we can have 4 different levels. This can give us a higher data rate, where m equals 4, sorry. But if we have noise in the system, then, good morning, then this scheme can lead to more errors. The idea of the role of the receiver is to take the received signal and map it to one of the possible levels. In this case, the receiver receives the signal and measures the voltage. Is the voltage close to -5? If yes, then we'll assume the received bits correspond to this level. If the received signal is close to +5 volts, then we'd assume that the received bits correspond to this level. If we introduce some noise, some random noise, with some noise in the system that the received signal is different from what is transmitted. If our received signal is now the red signal, the receiver takes a measurement, say it measures in the middle of the period. If it's, say, -5.6, the receiver compares. -5.6, what is it closer to, -5 or +5? -5, or we measure -5.6, which level does it correspond to, -5 or +5? -5, easy. So if we measure it here, although it's not exactly -5, it's closer to this than this. Therefore, we'd assume the bits which were transmitted correspond to this level. And here, even though it's not exactly +5, it may be +4, it's still closer to this level. Even with noise, even though the received signal is not identical to the transmitted signal, we would have no bit errors in this case. The bits received would be the same as the bits transmitted. Let's add the same amount of noise into this signal, or a large amount of noise. Now there's a larger chance that there'll be bit error. Why? Because the receiver takes a measurement, compares it to one of the 4 possible values. Whichever one is closest, it assumes they're the corresponding bits. Maybe in this case we measure here, we're lucky, we get -6. Okay, the closest is -5, we're correct. Maybe in this case we measure at this point, we get +2. And therefore the closest level is this one. And therefore the bits that we get from this will be corresponding to this level, not with the transmitted level. That would result in bit errors. So, although my noise is not exactly to scale, the point is if we have the same amount of noise in this case and in this case, there's a higher chance that there'll be errors using this signalling scheme, because we've got less tolerance for error. So increasing m increases our data rate if there's no noise, but in practice there is noise. So there are some practical limits on what the value of m could be. The larger m, the larger the impact of noise, and the more bit errors. We went through an example, I think, yesterday, which calculated the Nyquist capacity for a channel. Shannon came up with a different formulation which takes into account noise. Nyquist is very simple in that all we need to know is the bandwidth and the number of levels of our signalling scheme. And the signalling scheme, the number of levels you choose, is up to the designer normally. The person who designs the signal is sent can choose the value of m. But they need to choose a value which gives a high data rate, but is also not affected by noise. the shannon capacity takes into account noise. So the equation is the data rate, the maximum data rate, our channel capacity is the bandwidth of that channel, log base 2, 1 plus the signal to noise ratio, where the signal to noise ratio is simply some measurement of the signal strength, the signal power, divided by the amount of noise in the system or in the channel, SNR. So now we consider if the noise is larger, we'll see if the noise power goes up, everything else is fixed, SNR goes down. If we increase the value of noise power, then the ratio goes down, this value goes down, and our data rate goes down. It says, as we'd expect, the more noise, the slower we can send. The less information we can communicate. That's the same in this room. If everyone talks, if I'm talking at the same sound, the less information you'll be able to hear and understand, the less we can communicate. If the noise is very low and the signal strength is very high, then the data rate goes up. So this relates capacity, bandwidth and noise now. In practice though, so these 2 points can come direct from this equation. Increase the bandwidth or signal power, increases the data rate. Increase the noise, reduces the data rate. We see that from the equation. But there's some other trade-offs we need to consider. Increase the bandwidth normally allows more noise in practice. So those two factors cause some trade-off. You need to choose which one you want to consider. Also, increasing the signal power can cause more interference, which causes more noise, either intermodulation noise within the signal or against other signals. So it's not as easy as just increase the signal power or just decrease the noise or just increase the bandwidth. There's a trade-off that needs to be considered by the designers of the signals and communication links. To illustrate the Shannon capacity and bring these two together, an example, let's go through this case. We have a question taken from a quiz or an exam even last year. We have a channel. It has a spectrum between 3 megahertz and 4 megahertz. And we know something about the signal to noise ratio for that channel. It's 24 dB. That is, we've got this channel, we know the characteristics of the spectrum. We've done some measurements of the SNR, signal to noise ratio, and we measure it to be 24 decibels. The question is, how many signal levels are required to achieve the channel capacity? What are you going to do to solve this? Well, the question gives you some hints. So, right, it talks about Shannon capacity. First, we're going to need the equation for the Shannon capacity. Let's write down the information that we know. The equation B, the bandwidth, log base 2, 1 plus SNR. That's almost a hint in the question in that it says, how many signal levels are required to achieve the Shannon capacity? What do we know? We know the spectrum. Sorry, 3 megahertz to 4 megahertz. Maybe if we drew a plot of this signal or of this channel, the signals it lets pass, in practice it may look something like when we drew plots in the frequency domain, we just had impulses. In practice, signals contain multiple components or are continuous in the frequency domain. So a measured level of the signal that passes through this channel may look like this. It ranges from 3 megahertz up to 4 megahertz. So from that we know the bandwidth. The bandwidth is what? 1 megahertz. The width between here and here. What else do we know? We know it's given in the question that SNR in decibels, SNR dB equals 24 decibels. Shannon equation, Shannon capacity relates bandwidth and SNR. What's the question asked for? It doesn't ask for the Shannon capacity, it asks for how many levels do we need in our signalling scheme to achieve that capacity. And that gives us the hint of we're going to also need the Nyquist capacity equation, because that relates some capacity to the number of levels. Just to save space, we'll remove this. So we should be able to calculate the Shannon capacity. We know the bandwidth B, we know something about the signal-to-noise ratio. We'll need to come back to that in a moment. Then we could calculate the Shannon capacity, but the question doesn't ask you for that. It asks for the number of levels needed to achieve that. So we know something else, the Nyquist capacity, 2B log base 2 of m. This is what we want to find. We want to find what is the number of levels needed. And we could see now that, all right, our approach should be find the Shannon capacity based on B and the signal-to-noise ratio. So we know the capacity of our channel, we know the bandwidth, how many levels do we need at minimum to be able to support that capacity. So then use the Nyquist capacity to say, okay, if we know what capacity we need, we'll just calculate it here, and we know the bandwidth, then we could determine the number of levels that we need to achieve that capacity. So let's try and solve it. The one thing that was missing really is that the Shannon capacity, the signal-to-noise ratio, is an absolute value. The value given in the question is measured in decibels. We cannot put that value in decibels into the equation. The value in the equation is the absolute value. We cannot substitute it with the decibel value. So we need to know something about decibels. What's a decibel? Something about logarithms. If you look in your handouts, in one of the first documents, there's something about definitions and concepts. And one section gives a brief introduction to signal strength, decibels, gain and loss. So let's talk about that before we solve our problem, because that's important for this problem and also important for the next topic. This is the document. It's in the front of your handout, definitions and concepts. You've already read it because that was one of your homeworks. Something about units and prefixes, so if you can't remember them, go and have a read through there and understand the different prefixes that we use. Milli, micro, nano, kilo, mega, and so on. Your high school mathematics about logarithms. That becomes useful when we start to deal with decibels, because decibels use logarithms. And let's explain a little bit of how we're going to use decibels, especially when we talk about communication systems. We know with any communication system, we've already said that when we transmit a signal, it gets weaker over distance. it attenuates. So the strength of the signal when it's transmitted has some level, some power level or some voltage level, and when it's received is going to be less than the transmitted signal strength. So a transmission system, we transmit with some strength and we receive with some strength which is less. So often we'd like to measure this difference between what's transmitted and received, and we'd characterise this as some loss. We lose signal strength over distance through our communication system. So we'd like to have some measure of loss of the signal strength. Of course, sometimes we'll compensate for this by amplifying the signal. Our audio equipment, my signal comes out of my mouth at some level, goes through this audio system, reaches the amplifier, that increases the magnitude of the voice, increases the magnitude of the signal and transmits it to you. So we can have an amplifier inside our system which causes some, or introduces some gain. So we have a concept of loss and gain. Loss is a decrease in signal strength and gain is an increase. How do we measure it? Well, we could characterise our system quite simply. We have some input signal with some power. Let's say some power, the signal strength coming into the system is characterised by P in, the power coming in, and some signal comes out with a strength of P out, the power level of the signal. This system could be anything. It can be our communication system, it could be an audio system. We have some input signal and output signal. So if we want to measure the gain or the loss of that system, the absolute gain, or ABS for absolute, is simply P out divided by P in. If my amplifier takes 1 watt in and produces 10 watts out, then the gain is 10. It increases the signal by a factor of 10. The output divided by the input. In communication systems, we often convert this to a decibel form because decibels are easier numbers to deal with in many cases, especially when these gains and the losses, we'll see in a moment, are very large numbers. By taking the logarithm, we can deal with smaller numbers, which make it easier to do calculations in some cases. So how do we convert this to a decibel form? The gain in dB, 10 log the absolute value. And that's any decibel, whether we're looking at gain, loss, when we look at signal to noise ratio, 10 log the ratio of the two power levels. So, an example, our input power is 1 watt. We've got an audio amplifier and some system that produces 100 watts on output. So it's an amplifier in this case. It has some gain. The absolute gain will be 100. No units, it's a ratio of two power levels. So this is 100 times larger than the input. We increase the signal by a factor of 100. That's the absolute gain. The gain in decibels is 10 times log, sorry, maybe to make more clear. This is logarithm in base 10. 10 times log of the absolute gain. Log in base 10 of 100 is 2 multiplied by 10, 20 decibels, 20 dB. So these are the same values for our system. Our system has a gain of 100 or 20 dB. Just same values. This is expressed as an absolute ratio. This is expressed in decibels. Another example. So that was an audio system as an example, which amplified the signal. Our communication system, I transmit with some power level, 1 milliwatt. I've got a wireless device, a Bluetooth device, transmitting with 1 milliwatt. The signal gets weaker over distance. It's received with 1 microwatt. So here's a communication system. We start transmitting at 1 milliwatt, the receiver receives 1 microwatt. What's our absolute gain? Absolute gain, just take the output divided by the input. Remember, 1 microwatt is 10 to the minus 6 watts. 1 milliwatt is 10 to the minus 3 watts. So we get 10 to the minus 6 divided by 10 to the minus 3, which is in 10 to the minus 3. Just this number divided by this number. That's our absolute gain of our communication system. What's our gain in decibels? Again, we take the logarithm of this value. The log of 10 to the minus 3 is minus 3 multiplied by 10 minus 30 dB. The log of this is minus 3 multiplied by 10, we get minus 30 dB. This is the gain of our communication system. It's got a negative gain. What does that mean? It's a loss. A negative gain is a loss. A negative loss is a gain. So we could say that the loss in our communication system is 30 decibels. Or the absolute loss is 1,000. Our received signal is 1,000 times less than the transmitted signal. So the absolute loss is 1,000. The loss in dB is 30 dB. So we have loss and gain, and these are commonly used to talk about different aspects of communication systems. And we often deal in decibels. The loss, all right, we can write an equation. Loss is absolute loss, P in divided by P out. In this case, we start with this amount in, we end up with this out. The absolute loss is in the ratio as a factor of 1,000. The output is 1,000 times smaller than the input. And we can apply the same equation to convert to decibels. To convert the ratio to decibels, simply take the logarithm in base 10, multiply by 10. Log of this is 3, multiplied by 10. Our loss in dB is 30 dB. To convert between the decibel values, the gain is the negative of the loss, and vice versa. Minus 30 dB gain is 30 dB loss. And that's why sometimes it's easier to work in decibels. When we have multiple components, one component has a gain, one component has a loss, and another component has a gain in our system. So 1, 2, 3 boxes. Then when we talk about gain and loss, we can add up the decibel values. A property of our logarithms, if we need to multiply the absolute values, when we take the logarithm, we can add them up. And addition is much easier in my head than multiplication. So people often work in decibels when we talk about a communication system. Any other questions on that before we come back to our example about Shannon and Nyquist capacity? You should be able to convert power ratios to decibels. This is just a ratio of two power levels. And the gain, the decibel is 10 times the logarithm of that ratio. Any questions? Absolute gain has no units. It's a ratio. It's one level, or one power divided by another power. So the units of the power, which it may be in watts and watts, cancel out. So it's a ratio between two values. So there are no units there. Okay, so we need that knowledge to come back to our question, which says we have a signal-to-noise ratio expressed in decibels. Our question gave us the signal-to-noise ratio in decibels. But the Shannon capacity equation, this value of SNR is the absolute value. Remember, SNR is a ratio between two powers, signal divided by noise. So we need to convert SNR dB into the absolute value. That's why I use the subscript dB here to say that this is a different variable than this one. The absolute SNR, let's write it differently. The SNR in decibels is 10 times the logarithm in base 10 of the ratio of two powers, the signal divided by the noise. So if this is the absolute value, the value in decibels is just the log of that multiplied by 10. We know this, 24 equals 10 log base 10 SNR. Therefore, you just solve for SNR. What is SNR now? 10 to the power of 2.4. The one with no subscript. SNR in the Shannon capacity is the absolute value. SNR dB is the decibel value. A little bit confusing, we use the same SNR. So in this equation, SNR dB is one variable. SNR on its own is another variable. This is the value in the absolute, or this is the absolute ratio. This is the value in decibels. And this is the same equation that we have over here. The general decibel equation, 10 times the logarithm of two power levels, the ratio between two power levels. In gain, it's 10 times the logarithm of P out divided by P in. In loss, 10 times the logarithm of P in divided by P out, and so on. 10 times the logarithm of our signal divided by noise. We know this is 24. Bring the 10 to the other side and we get 2.4. 2.4 equals a log of SNR. Therefore, SNR equals 10 to the power of 2.4. If you can read this, I'm running out of space. SNR equals 10 to the power of 2.4. Just solving this equation. Use your calculator, and it's about 251, because I've solved it before. 10 to the power of 2 is 100. 10 to the power of 2.4 is about 251. Okay? So you need to be careful. The Shannon capacity uses the absolute value in here. You cannot put 24 decibels in this equation. It will not work. It will not give you the right answer. We needed to convert it to the absolute value. And also be careful. Decibels log in base 10 these two equations of capacity log in base 2. Different base there. Now, what do we know? We know SNR. It's 251. We know B. It's 1 megahertz. We will calculate the Shannon capacity direct from that equation. And that's our desired data rate, our desired capacity we'll calculate. And because we know our desired capacity, we know our bandwidth, we can calculate the number of levels needed to achieve that capacity. Let's go through that. First, we'll calculate the Shannon capacity. So, with our bandwidth of 1 megahertz, which is 1 by 10 to the power of 6, 1 megahertz, log base 2, 1 plus SNR. Okay. Any questions?
We have problem about
yeah, high school mathematics is hard if you don't remember it. So in that handout there's some very basics about logarithms. Go back and refresh your memories. And simple solving equations. Refresh your memories and you'll be able to do them much faster. And you'll be easier to follow the lecture examples and you'll have more time in the exam and quizzes. So this is what we get. So we can solve for C, the capacity. Log in base 2 of 252 is what? Approximately. Use your calculator. Calculator doesn't do it, does it? It doesn't have log in base 2. 7.9 is correct. Why? If it was approximately, if it was 256, 2 to the power of 8 equals 256. Therefore, log in base 2 of 256 would be 8. We have 252, so it's going to be slightly less than 8. Only a little bit less. Remember, it's logarithm. So I think it's 7.9 something, 7.97. I will make life easier and say approximately. It's approximately 8. It's a little bit less. So we get 8 times 1 times 10 to the power of 6 is 8 megabits per second. This is about 8 times by 1 million, 8 million bits per second. Remember the capacity measured in bits per second. Now your calculator, when you want to get, if you cannot get an approximate answer, you cannot guess it, then how do you solve it in your calculator? Again, that's in the lecture notes or in that handout on logarithms. Your calculator does log 10. Log in base 2 of x is the log of good. If your calculator only supports log base 10, then this is a useful formula. The log, in fact, it's not just for log 10 and log 2, it's for any base. If you want to calculate log base 2 of some value, calculate a log base 10 of that value and divide it by the log in base 10 of the base here, 2. And you'll get the answer. So that's shortcut if your calculator doesn't support log base 2 directly. That's in the handout. That's your basic logarithm high school mathematics. We know the capacity is around 8 megabits per second. We know the bandwidth. We want to know how many levels do we need to achieve that bandwidth. What signalling scheme should we use? If we want to get 8 megabits per second, instead of mega, I'll write 8 by 10 to the power of 6. According to the Nyquist equation, 8 megabits per second is 2 times the bandwidth. Our bandwidth is still 1 megahertz. 1 by 10 to the 6 log base 2 of m, which says that if we have this bandwidth and we want to achieve this capacity, we need this m number of levels. 2. Let's solve. 8, bring this to the other side, so it becomes 8 by 10 to the 6 divided by 2 by 10 to the 6, which is just 4. Therefore, m equals 16. Log of 16 in base 2 is 4. 2 to the power of 4 is 16. So it says, if we want to achieve this data rate, and we have the bandwidth of 1 megahertz and this SNR of 24 dB, then we need at least 16 levels. If we had less, if we had 8 levels, then we'd get, if m was 8, we would get just 6 megabits per second. We could not achieve the Shannon capacity. So in this, the answer, we need at least 16 levels to achieve this capacity. So it can be used as a rough design rule to work out, okay, how many levels do we need when we design our signal? Any questions about how to solve that? It brought our two equations together. So we saw examples of both. One more example. Okay. Okay, so we'll go, for the rest of the lecture, we'll go through some other examples. So that brings us to the end of this data transmission. What we're going to do now is go through different examples from past quizzes, and you will do them. First one. And we, not that one. We're going to go back. We'll do some examples if we get time about Nyquist and Shannon, but first go back to our very basics about signals. Answer this question, or think about how you would answer it. And part B, the second part, is what is the bandwidth of that signal? Right now, answer that. Everyone's finished with this? We have a signal, some equation for that signal. Draw the plot of the signal in the frequency domain and answer what is its absolute bandwidth. So this is going back to the topic we covered even last week. If I asked you a question to draw a plot in the time domain, then that would be hard without a calculator or some computer to calculate. But in the frequency domain, it should be easy for you to draw a plot of that. We have 3 sine components. You need to identify the frequency of each of them. Component 1, 2 and 3. So the first component, how do we work out the frequency component? We remember our general equation. 2 pi the frequency t plus the phase. The phase is 0 in all of these. 2 pi ft. Well, we have 60 pi t in the first component, which means 60 pi t, if we equate it to 2 pi ft, pi cancels out, t cancels out. 2 times f equals 60, f equals 30 hertz. The frequency of the first component is 30 hertz. What about 200? F2 is 60. The frequency of the second component, same approach. Simply 120 divided by 2 in this case, 60 hertz. And the last one will be 100 hertz. So they are the frequencies of the individual components. We need a plot of the entire signal, which is the summation of those components. What do we do? Find what?
The basic one is the low frequency.
No, I don't think we need that at this stage. First, you need a plot.
Plot ก็คือเอา frequency แล้วก็ intensity มา plot.
A plot of the frequency against the peak amplitude, usually measured in volts or some power level. And we have an impulse for each component. So at 30 hertz, we have a peak amplitude of 10. The first component is 10 times sine. Uppercase A is 10. This is the peak amplitude of that component. Volts here. Volt V. Voltage. Some power level, some measure of signal strength. Remember, with everything the same, volts and watts are proportional. Second component, 60 hertz, and amplitude of 5. That's 60. And the third component, 100 hertz, amplitude of 2. So that's our answer to part A. Real signals, or many communication signals, are not as simple as this. We're just having 3 components. When we measure them, we see something where we have a continuous frequency domain plot, similar to one I drew earlier today. It may be something like this. It's not as straightforward as just having a fixed number of components. But the same concept applies. We have some minimum frequency component and a maximum. And from the minimum and maximum frequency component, we can calculate the bandwidth, the width of the spectrum that that signal occupies. This signal occupies frequencies from 30 up to 100, gives us a bandwidth of 70 Hertz. The maximum frequency component minus the minimum. So the second question, or part B down here, was what was the absolute bandwidth of that signal? It's easy to determine from here or from this information. If we have many components, like this case where we have many, then the same concept applies. The bandwidth is the portion of the spectrum that the signal occupies, which ranges from the minimum frequency component to the maximum. Normally in real life, when we look at the next topic, we'll talk about different parts of the spectrum, but to avoid interference, we transmit a signal with a particular bandwidth at some portion of the spectrum. If we transmit another signal at the same bandwidth, same portion of the spectrum, they will interfere with each other, and that causes problems. So normally our signal, if someone else is transmitting at the same time, needs to use another portion of the spectrum. And that's why bandwidth has some cost incurred. It's a limited resource. The more you use, the more it's going to cost, because there's only a limited resource to be shared by everyone in the world, and therefore there's some cost assigned to using that. The more you use, the higher it's going to cost. And the cost is sometimes not measured financially, but we see if it's free, then we get interference. But we'll cover that in the next topic. That was an easy quiz question. So something like that, you need to solve in like 3 minutes. You need to identify, okay, frequency components, the frequency, draw the plot. Another similar question, which you'll solve in 3 minutes. Here's another signal. What's the period of that signal? And what's the absolute bandwidth of that signal? Maybe the absolute bandwidth will be easier for you to calculate because it's similar to what we just did there. Try that. So maybe try part B first. What's the absolute bandwidth? Anyone have an answer to either part A or part B? Don't worry too much about writing down the questions, solve the question. The questions are available on the website for the quizzes last year. It's easier. We'll see next week when you take it.
No, I mean easier than
Yeah, I understand. Yeah, some of the calculation questions are easy. Yeah.
especially the definition is hard.
Who's got an answer to either of parts? Period or absolute bandwidth of this signal? Have an answer?
Yeah.
Part B?
Yeah.
What's your answer?
12 megahertz.
What is it?
Bandwidth is 12 megahertz.
20. 20 megahertz. Absolute bandwidth is 20 megahertz. That's correct. See if you can get that answer.
Point to microseconds.
And period, 0.2 microseconds. That's correct. Let's part B first. They're both related. In both cases, we need to know the frequencies of each component. Frequency of component 1 is what? 5 megahertz. It's 10 times 10 to the power of 6 pi t, or 10 million pi t. Our general form is 2 pi ft. So if we divide that 10 million by 2, we get 5 million, or 5 megahertz. Component 2, 15 megahertz. And 3, 25 megahertz. 50 million divided by 2 gives us 25 million, 25 megahertz. They are the frequencies of our 3 components. So, what's the bandwidth? Same. 25 minus 5. It's the maximum minus the minimum. We're ranging from 5 up to 25. We occupy a bandwidth of 20 megahertz. 25 minus 5. So that's part B, easy. What's the frequency of the signal? What's the frequency of this signal from... Well, we don't have it anymore. Let's not say that. Why is the frequency 5 megahertz? The fundamental frequency. In this case, the 3 components are all multiples of 5 of one of the others. This is 1 times 5. This is 3 times 5. This is 5 times 5 megahertz. Which means, if that's true, then it means that 5 megahertz, this one is the fundamental frequency. And it's the resulting frequency of our signal S of t. That is, the signal when we add the 3 together has the frequency of 5 megahertz, the fundamental frequency. In the previous question, that wasn't true. Remember, we had 30, 60 and 100 hertz. They were not all multiples of one of the components. If this was 90, it would be, but it was in fact 100.
So it's 3.33 times.
Yeah, we're not multiples of this, one of the component frequencies. That's the definition of the fundamental frequency. Multiples of one of the component frequencies. In this case, if this was 90, the fundamental frequency would be 30.
So it has no fundamental frequency.
Yeah, so the frequency of the resulting signal we cannot directly infer from this information. We can determine the frequency. If you plot the signal, you'll see the frequency. In this one, we can quickly determine the frequency because all of the components are multiples of one of the components, or all the others. These are the harmonics, this is the fundamental frequency. And the resulting signal has a frequency of the fundamental frequency. We say this one's the fundamental, and these are harmonics. Harmonic frequencies. But the fundamental gives us the frequency of our resulting signal, and the period is the inverse. 1 divided by 5 million. 1 divided by 5 million is 0.2 microseconds, our period. So we can relate those factors together. Period is always the inverse of the frequency. If you know the frequency, you get the period. But sometimes we cannot easily get the frequency of the signal. In the second question, we could. Any problems? If we have a surprise quiz at the end of the lecture, you'll be okay?
Oh no.
Another example. There's our question, and it's what is the maximum data rate possible? We have an encoding scheme that maps 3 bits of digital data into one signal element. If our channel is noise-free, has a bandwidth of 200 kilohertz, what's the maximum theoretical data rate possible? The question, although it doesn't not shown there, it says theoretical, because the Nyquist capacity and even the Shannon capacity give us a theoretical maximum data rate. In practice, there are other limitations that mean we cannot quite achieve that theoretical data rate. Well, they give us an upper limit. What is that upper limit in this case? Anyone have an answer? What's our data rate in bits per second? .2 megabits per second, that's correct. Keep trying. Try and solve. Okay. Try and solve it yourself. Which equation are you going to use? Which capacity equation? Nyquist. Why? Well, the question gives you the hint. Noise-free. Nyquist assumes the channel is noise-free, which is never the case, but to keep things simple, that's the assumption that model takes. And the other hint is the information given to you. The question gives you the bandwidth and says something about the signal elements. You need to work out how that relates to M, the signal levels. It says nothing about signal to noise ratio. It says nothing about noise. So we need the Nyquist equation. So you need to know the Nyquist equation. B, 200 kilohertz, that's easy. We want to find C, what's M? M is 8. Why is M 8?
3 bits.
Yeah, 3 bits of digital data mapped into one signal element. So if I want to transmit, so what that means is when we want to transmit digital data, a sequence of bits, if that's our data we want to send, our scheme to map the data into a signal takes 3 bits, and that maps to one of 8 different levels. Why 8? Well, the optimal scheme, if we're going to work at 3 bits at a time, has 8 different combinations. So to transmit these 3 bits, I would send at the signal level corresponding to here. If we're using discrete digital pulses, then these may be some voltage level, whatever, +5, +4 volts, +3 volts. Doesn't matter the absolute values. -3, -4. That is, each combination of 3 bits corresponds to one signal element, one level of the signal. With 8 levels, m equals 8. And our equation becomes 2 by 200 hertz. That's 200 k hertz. Kilo, 10 to the power of 3. Log. Gives us 3. The log of 8. If we have binary values and we have 3 binary digits and we get 8 combinations, 8 levels. Log of 8 is 3. 3 times 2 times 2 is 1200 kilohertz. .2 megabits per second, if you work out all those zeros. So you need to be able to identify what equation to use in that case. How can the data rate be increased without increasing bandwidth? Okay, easy. If we cannot increase B, the only way to increase C is to increase the number of levels, M. What's the problem of doing that? More errors are possible. More levels, the more chance that when we really have noise, that the receiver will make a mistake. It will receive a value of the signal. It will measure at minus 3.7 or plus 3.7 volts, okay, because there's noise, and then it maps it to this value when in fact it was this value that was transmitted. So the more levels, the more chance that some amount of noise will cause bit errors or cause errors. I think that was the second part then. The disadvantage of increasing the data rate by increasing the number of levels is that more errors can occur. Going back to the other quiz, I think we have one more question. Easy one. What's the data rate possible? We receive a 4 megahertz signal with power level 150 milliwatts. The communications channel has 10 milliwatts of noise. What's the theoretical data rate that we can achieve with this communications channel? Try and solve that. (16 megabits per second). Good, correct. Spend your time solving, not writing the question down. Okay? You can always find the questions later. There's It's not so important. 'And if you know the data rate, find out the signal-to-noise ratio in decibels. Yes, so in this case the signal, when we simplify and say we receive a 4 megahertz signal, it means that signal occupies a bandwidth of 4 megahertz. So often we'll omit talking about bandwidth, meaning that that's the bandwidth. It depends a little bit on the context of the scenario. What equation are we going to use? Whose equation? Shannon's equation? SNR. B is, in this case we assume it's a 4 megahertz bandwidth signal. 4 by 10 to the 6 hertz. SNR is signal to noise ratio. It's the signal power divided by the noise power, a ratio of the two. Signal power 150 milliwatts, noise power 10 milliwatts. It's a ratio of two power levels, so the units cancel out. 150 divided by 10 is 15. Signal to noise ratio is 15. So we get C equals 4 million, 4 by 10 to the 6, log base 2 of 1 plus 15. 1 plus the signal to noise ratio, which is 16. Log of 16 is 4. 2 to the power of 4 is 16. 4 times 4 this is 4 times 4 is 16 megabits per second. Last question, what's the signal to noise ratio in decibels? Fourteen. 40 decibels. 15, 15 I think you're close.
Of 15 multiply 10.
Okay. So remember, decibels is just 10 times the logarithm in base 10 of the power ratio. So our ratio of power levels is simply signal divided by noise, which has a value, absolute value of 15. Convert to decibels, 10 log in base 10 of the ratio. Or more precise, 150 divided by 10. So log in base 10 of 15 is 1.17, multiplied by 10, 11.7 dB, approximately. All right, just to calculate that, that's where you need your calculator to get the exact value. But you need to know the procedure for calculating that. So, your practice or your homework is to, of course, everything that we've covered in that topic, but also understand about decibels and the conversion between the absolute value and the decibel value. That's important. What do we do to increase our data rate? Assuming noise cannot be controlled. Sometimes noise in a channel we cannot control what it is. Can't change the bandwidth. What do we do? Increase the signal. If we look at the equation, we can't change B. Let's say we have a channel with a fixed bandwidth. We cannot control the amount of noise in that channel. So N in the signal to noise ratio. If we want to make C larger, increase the signal strength. Signal to noise ratio goes up, C goes up, the capacity goes up. So just a relation, or just identifying those components inside the equation here. And I think that's it. Any questions on any of this? There'll be a quiz next week. I don't know which day. The next topic we cover is transmission media. Okay. Any questions? Everyone can answer the quiz questions.
The signal power, we only signal power.
Yes. In this one, the answer, if you increase the signal power, the signal strength, in theory you can increase the data rate.
Does it have any disadvantage of increasing or off?
Increasing the signal power in practice is not so good in some cases. If you increase it too much, you can overload the receiver circuitry. If I talk very, very loud, then it may hurt your ears. Same with electronics. If you send a signal that is too loud, the receiver circuitry may be overloaded and cannot understand anything. Also, if I talk very loud, the people out there are interfered with. So we can cause interference with other people communicating. So in real life, we often have to control the signal strength. There are limitations. In theory, increasing it here increases our data rate. Any final questions? Finished for today. Next week we'll start on the new topic of transmission media.
And one quiz.
And one quiz.